Hey everyone, and welcome to This Explainer. Today, we're diving into something truly fascinating. We are unpacking a foundational blueprint for teaching machines exactly how to think, learn, and solve complex problems. We're going to look at a highly structured curriculum that lays out how artificial neural networks are actually designed to operate from the ground up. By the end of our time together, you'll have an incredibly clear, high-level map of the entire journey required to build and truly understand these amazing systems. Let's get right into it. Here's a quick roadmap for where we're headed. We'll cover the objective of network learning, foundations of neural models, supervised learning algorithms, unsupervised and reinforcement learning, and finally, application and problem solving. Starting off with Section 1, the objective of network learning. Before we start playing around with algorithms, we need to know what the end goal is, right? And the crucial point here is that this isn't just about memorizing some abstract computational theories. The source material states it perfectly. To apply the learning to a network also expected to analyze and interpret the result. So this objective is highly active. We aren't just firing data into the void. The real goal is to practically apply that learning to a network structure and then, crucially, actively analyze and interpret the results we get back. It's all about creating a feedback loop of genuine understanding. Moving right along to Section 2, Foundations of Neural Models. Now, the curriculum starts by mapping out the fundamental types of learning. But if you really want to grasp modern AI, you've got to look at the historical building blocks first. The text specifically calls out the Mikulicz-Pitt model, which was huge because it introduced the idea of binary thresholds for computation and the Hebb network. You know, the famous rule that cells that fire together wire together? These are literally the earliest conceptual models of artificial neurons. They represent our very first attempts to mathematically replicate how biological brains connect and fire. Getting a handle on these gives you the essential scaffolding for everything else we're going to talk about. Alongside those early models, there's a heavy emphasis on a concept called linear separability. Now, this is absolutely foundational. We have to grasp this if we want to understand the capabilities and, let's be honest, the hard limits of those early neural models. In simple terms, understanding linear separability tells a developer right off the bat whether a specific problem can be solved by a basic, simple neural network or if it's going to require a much more complex, multi-layered architecture. It's the ultimate test of a network's potential. Okay, Section 3, Supervised Learning Algorithms. Now that we've got the foundation, how do we actually teach the machine? The curriculum breaks machine learning down into distinct categories, mainly highlighting the massive contrast between guided, supervised techniques and unguided, unsupervised systems. With supervised learning, it's pretty straightforward. You give the network the answers along with the questions so it can learn the relationship between them. Basically, you are the supervisor actively guiding the learning process. Under this supervised umbrella, we get a very specific, incredibly powerful toolkit. You start with the perceptron, moving from simple single layers up to complex multi-layer setups. Those are exactly what you need to handle those non-linearly separable problems we just talked about. From there, it introduces the delta learning rule to mathematically minimize errors, and then the big one, the backpropagation algorithm. Backpropagation is essentially the core engine of modern deep learning. It's what allows a network to adjust its own internal weights based on the mistakes it makes. It is a phenomenal sequence of guided instruction. That brings us to Section 4, Unsupervised and Reinforcement Learning. So, what happens when we take the training wheels off entirely and let the network find patterns on its own? For unsupervised learning, our source text mandates studying techniques where the system has to find hidden structures in completely unlabeled data. We're talking about the winner-take-all approach, self-organizing maps, and learning vector quantization. In these scenarios, nobody is telling the network what the right answer is. Instead, it organizes the data entirely based on its own discovered similarities. It's a wildly powerful way to process raw, unstructured information. And to completely round out the major pillars of machine learning, the contents also include an introduction to reinforcement learning. Think of this as learning by trial and error. The network navigates an environment, makes decisions, and then receives rewards or penalties based on its actions. It's the final piece of the core conceptual puzzle in this curriculum. Finally, Section 5, Application and Problem Solving. Now, what's genuinely exciting about this final stretch is how we transform all these academic concepts into actual actionable skills. Because let's face it, theory is pretty useless without practice. The curriculum explicitly requires a tangible demonstration of these learning techniques using an open source tool. That proves these concepts aren't just math on a chalkboard. They actually work in the real world. By utilizing open source tools, you can directly interact with the algorithms, tweak the parameters yourself, and watch the learning happen in real time. But the curriculum doesn't just stop at classroom instruction. It also designates PAC learning, which stands for Probably Approximately Correct Learning, as a specific self-learning topic. This is perfect for those looking to expand their independent study. It pushes you to understand the mathematical frameworks behind exactly how much data and computing power you need to guarantee that a machine has actually learned a concept. Ultimately, this entire blueprint guarantees two very specific, highly practical outcomes. Step 1, successfully applying artificial neural concepts to solve a problem. And step 2, taking the specific learning methods we've unpacked today, supervised, unsupervised, and reinforcement, and executing them to solve problems in the real world. The whole shebang is about moving from a conceptual design to practical, hands-on execution. We've covered a ton of ground today. We've unpacked the historical foundations, the supervised training wheels, unsupervised pattern recognition, and the absolute necessity of applying all of this to real-world problems. So armed with this complete blueprint of a machine mind, I want to leave you with one final thought as you step out into the world of neural networks. With open source tools and these advanced learning algorithms at your disposal, what problem are you going to solve first? Thanks so much for joining me for this explainer, and keep learning.